Okay, so part of our work is going to be taking a function like, say, y equals 3 plus x, okay, and finding its inverse. So we'll follow our same procedure to find the inverse. We'll switch the x and the y, and then we'll solve for y. So if we do it, we'll get 1/3 x minus 2 equals y. So our claim at this point is that the inverse of 3x plus 6 is 1/3 x minus 2. And again, you can check that by table, by graph. If you graph these two and see if they look like they're reflections over the line y equals x, you could be convinced. If we put in a number like, let's say, 10 into that, if we put 10 in here, we're going to get 30 plus 6, that's going to be 36. Okay, and if you look at the inverse, if we put 36 in, we're going to get 36 times a third, which is 12. 12 minus 2 is 10. So you can convince yourself with table or graph that they are in fact inverses, but really the only way to prove it is by using algebra. Okay. Now here's the property that we need to use to prove that they are inverses of each other, and we're going to use what we call the inverse composition rule. Okay. So if f is 1-to-1 with an inverse function g, and again, keep in mind, it doesn't have to be 1-to-1 if we restrict the domain. So like the parabola, we can still do this technique with, okay, as long as we have a domain restriction on there. But what it boils down to is if we take f and g, if these two are inverses, okay, if f and g are inverses and we compose them, okay, put one into the other, and we get x as an answer, okay, that would be good. Okay, but we also have to put the other one into the original, okay, and show that that equals x also. Okay, and remember, the reason why we'd have to do this is because when we did compositions in the last chapter, okay, did every time we did f of g and g of f, did we get the same answer every time?
No.
No. Okay, this is not a commutative operation. It's not necessarily the same f of g as g of f. Okay, so that's why we have to show it true for both ways. Okay, and so here's what that's going to look like in action. If I want to take my two that I think are inverses of each other, my claim is that they're inverses, okay, then I should be able to put the inverse function into the function, okay, and get x. Well, let's find out. If I do 3 times 1/3 x minus 2 plus 6, again, I'm taking the inverse function, plugging it into the f function, and then when I do the math, I'm going to get x minus 6 plus 6, which is equal to what? X. That's good, but it's only half good. Okay, we have to do it the other way also. We have to do the inverse, okay, with the function plugged in. So if we do 1/3 times 3x plus 6 minus 2, so again we're taking f and we're putting it into the inverse, and we distribute again, we're going to get x plus 2 minus 2, which is what? X. Okay, and again, that's what we want to have happen. Okay, if these are inverses, okay, when we compose them both ways, we're going to get x. Fair enough? Okay, if we do it right. Okay, and if it doesn't turn out to be x, then either you made a mistake or they're not inverses. Okay, because we might have a question. Could we have a question that says, okay, tell whether these are inverses or not, and then we have to do that and show whether they are or not? Sure. Okay. All right. So let's revisit those two functions that we had talked about earlier. So the f of x we said was 2x over x minus 1. So we can see this one more time. Our claim was, and we think it's true because of table and graph, that the inverse of that is x over x minus 2. Okay, so our claim is that these two are inverses with each other. So let's do the algebra to show that they are or they aren't. If we take the inverse function, which is x over x minus 2, and we plug that into the f function, it would be 2 times x over x minus 2 on top, and then it would be x over x minus 2 on the bottom. Whoops, I lied, minus 1. Alright, so we'd have this, and again, it's the f function with the f inverse function plugged in for x. Okay. Alright, now, if you look at that, that doesn't look like x to me. Okay, but it is, as we'll find out. Because when we have a complex fraction, remember the technique here we need to use is we need to multiply both top and bottom by the common denominator that's making this complex. So in this case, the only fraction we have on the bottom, if you will, is x minus 2, so that is the common denominator. So let's see what happens when we multiply these two. Okay, when we multiply this by this, what's going to happen with the bottom here and the top here? Yeah, those cancel out. And remember, they better cancel out or we did something wrong. That's the whole point of doing that. We want the fractions to be where? Gone. We want them to be out of there. Okay, so that's the whole point in picking that number to multiply by, or expression, or whatever it may be. So when we do that one, here's where we have to be careful though, because this time we're multiplying by a binomial, if you will. Okay, and so therefore we got to multiply twice. And so let's take care of this one first. If we do x minus 2 times x over x minus 2, then we're going to be left with what? X. Okay, minus, and then I'm going to put this in parentheses. When I do 1 times x minus 2, that's going to be 1 times x minus 2. And when we combine like terms on the bottom, remember we're subtracting both of these quantities. So we're going to wind up with 2x over, what's going to happen when I do x minus x? Gone. And if I do negative 2, that's going to leave me with a 2. And so really, what's the answer? It's x. Okay. And is that good? Yeah, definitely. Okay, questions on the algebra parts?
Why did you times x minus 2 by the 2 on the top?
Well, ultimately I multiply, I mean, this is all really one sentence right here. I mean, I could have rewritten this in the first place as 2x over x minus 2.
Oh, okay.
And if I multiply that by x minus 2, we're still going to get 2x like I got here. So it's, I really essentially did, but I just multiplied it by the x here. Okay. All right. Now, like I said, what does that prove? Okay. So remember, we were trying to prove that these two are what? Inverses. Have I done it already? No. Okay. We're not done. Okay. One way is not good enough. Okay. We got to do it both ways. So if we take our two functions and we do f inverse of f this time, okay, we need to show that that works the other way as well. So this time my function here was, my f inverse is this one. So I'm going to take that stuff and plug it into this one. So I'd have on top 2x over x minus 1. On the bottom, I'd have 2x over x minus 1 minus 2. Okay. And again, clear the fractions. Okay. And so gone with the x minus 1s, I'd be left with 2x on top. If I distribute the x minus 1, that's going to wipe out this x minus 1 and leave 2x for that part. And then I need to multiply minus and then 2 times this stuff, so 2x minus 1. Okay. All right. And let's see. Nope. Where did I miss? Oh, 2x minus 2. Thank you. Good. I was going to say that wasn't gonna cancel my 2. So again, subtracting these two. If we subtract these two parts, we'd have 2x on top. Again, same deal. The 2x minus 2x part would be gone. But then we're also subtracting negative 2, which would give us positive 2, which ultimately equals x. Okay. All right. So again, what did we just do? We proved that these two are in fact what? They're inverses. Okay. All right. Like I said, we could be convinced by graph and table that they're inverses, but the only way to prove that they're inverses is by composing them both ways, showing that the answer both ways is x.